Hello everyone, I'm Javeria and now I will present the design of a low-power high-gain observer for the wake flow rebuild. This work is co-authored by Matthieu, Estelle and Mr. Youssoufi. I'll start with a brief overview of my presentation by introducing the model of the system and the motivation behind the current work as well as the problem statement. Then in order to solve the problem, the design of the low-power observer is present and discussed in detail, and the results are verified through the simulations. For the end, I will talk about the future perspectives that are currently under investigation. So starting with the introduction, the flow at the back surface of a bluff body is a common occurrence, and the behavior of this flow depends on the Reynolds number. As can be seen from the figure, the flow separation at the front edge and the turbulency in the behavior can be seen for this high Reynolds number. And these big structures, which are called as the vortex shedding, appears at the rear surface of this bluff body. The changes of this vortex shedding thus leads to a significant pressure drop. Therefore, the control of this vortex shedding is then of major interest. The active control of the fluid mechanics is a promising and challenging research field, as if we were able to decrease this drag force, we can minimize the energy consumption of the vehicles as well as for the aerodynamical and the naval applications. And challenging because it requires the observation and the control for which our model tends to be should be real-time tractable and robust. And another challenge is because when trying to kill some modes in the wake flow to reduce the drag or to reduce the vibrations, then the other modes that contain the previously few energy will tend to rise. So therefore the flow control requires estimation. And therefore in this work we will focus on the design of an observer which is efficient and robust. So first we have considered a Gherkin model to model the dynamics of the vortex sheddings, and as it has already been proven to be a good compromise between the simplicity and the robustness. The unsteady flow is then approximated using the orthonormal Gherkin series, and where we have the steady state flow, and then we have the Fourier coefficients and the velocity modes. So in this study, we have considered two Gherkin representation. The first one is the minimal Gherkin representation that models the first two modes, which are the dominant modes, and it contains almost 95% of the perturbation energy. After it is followed by the shift mode that represents the energy exchange between the mean flow and the oscillatory perturbation. And then we have the growth rate parameter, which is constant and unknown for this model. And now we define a more refined Gherkin representation, which is referred as the hybrid model, where we have included some higher temp modes A3 and A4 that interacts with the main modes through the shift mode. And here we have an extra damping term, which is the mu prime. And so using the oscillatory amplitude, we define the dynamics of these the two dynamical models, which are of order 3 and 4 respectively. And for the output, we have y is equal to x1, which is available for both of these models. So for the estimation, we first study the observability of our system using the output y, where but from the expression, we can see that we suffer from some observability singularity, particularly when x1 is 0. And since the control aim is to bring the amplitude of the vortex shedding to 0, meaning to make the dynamics of x1 go to 0, therefore we need to deal with this singularity and make our system observable. So therefore, we study the standard approach of a high-gain observer, but it has some flaws which needs to be addressed properly. The first flaw is related to the increasing power of the high-gain parameter that causes the sensitivity issues. And the second is about the requirement of the non-singular diffeomorphism, which is no longer possible in our case because the system suffers from the observability singularity. So now we propose some solution for these flaws. And first, we rely on the work of Estolfi and Marconi. And we will be able to limit the power of this high-gain parameter up to the power of 2 regardless of the system dimension. And for the second, in order to deal with this observability singularity, we can add some fictitious outputs in our system. And the core idea of this observer is based on the work of Andrew and Bahmat. So here we define the standard low power observer, which clearly has an increased dimension. But despite the increased dimension, the advantage of using this observer is twofold. First one is the limited innovation term predominance, and then its reduced sensitivity to the output noise, especially at the high frequencies, which is of major interest as we are dealing with the wake flow. So we can obtain the low power observer in the natural coordinates, but it should be provided that phi is a diffeomorphism, but the invertibility of now this matrix is no longer possible when we will have the singularity in our system, and here it represents the dynamics of the new observer. So now we provide the main results in which we follow a systematic way by proposing a three-step procedure. In the first step, we do the augmentation of the real mapping to make the dynamics equal to the dynamics of the low power observer. Then to propose then we propose the extension in order to solve the issue of the observability singularity. And by extending the states, and here we have the new mapping, which is given by phi e. And for the last step, we tend to go back to the natural coordinates and by augmenting our extended system into a global diffeomorphism given by the bold phi. This approach is then applied and explained with the help of an example, and we take our minimal system and obtain the z dynamics in the usual way. After this, we build the low power observer for the system, and here it has an increased dimension. So we tend to follow the first step and do the augmentation of the mapping, and we obtain this new mapping phi a, which is defined for the minimal system. And here we have an additional state variable x2 prime. And similarly, for the hybrid system, the process is done, and we obtain a new mapping phi a, for which we have the two new state variables added, the x2 prime and x3 prime. So the Jacobian of this augmented mapping is given by the matrix J, which for the minimal system is given and has the determinant, and for the hybrid system it is given, and similarly it has a determinant value expression given here. The invertibility of this Jacobian is now possible as long as the extended state stays away from the singularity, yet there is no guarantee that it will stay away from the singularity. So therefore, the next step addresses this concern. So in this step, in order to avoid losing any excess of the other state variables, when we have the singularity, we introduce some fictitious outputs in our system, where we have we introduce 3 fictitious outputs for the minimal system and 6 for the hybrid system. And these are defined by the continuously differentiable functions of rho and rho prime, which by construction we have chosen to be null everywhere except when we have the singularity. So by adding these fake outputs into the augmented Z state vector, we can define the extended Z dynamics over here. And the Jacobian of this extended mapping is given, where we have the matrices J and JF. So J is defined in the previous slide. And here we define our matrix JF, which depends on the functions of rho and rho prime. And since by definition, these two matrices cannot be single simultaneously, therefore the Jacobian of this extended mapping has a constant rank Q for all XA. So now we have successfully removed the observability singularity, but it requires diffeomorphism to get the observer in the natural coordinates. And to do so, we extend the system into the global diffeomorphism by adding the exogenous variable to the augmented X state vector. And the extension is done in the Z dynamics by which is further completed by adding the psi columns. And these psi columns are basically composed of zeros, ones, and x1. So by differentiating this mapping, we obtain the Jacobian of the new mapping, and the determinants of the both systems for the minimal system and for the hybrid system is given. And by construction of the functions of rho and rho prime, these Jacobian determinants are strictly positive. So therefore, the observer is well defined, and we get the global diffeomorphism for our system. So now we tend to go back to the natural coordinates, and the low power observer, which is able to avoid the singularity, is given, where epsilon being the Marconi low power observer and Kp being the positive definite gains for the fictitious outputs. We can get the dynamical model for the system, and from the proof we get that phi e is injective, and it defines a converging observer, meaning that when time tends to infinity, the estimation error asymptotically converges to 0, which is further verified through the simulation results. And for the first set of simulations, we applied the proposed Huygens observer for the minimal system in the natural coordinates. And here we have the system states, the estimated states, and the estimation error. Some peaking effect can be seen during the initial time. And this happened because we initialized our state x1 at 0, and thus forcing the system to be singular. And therefore, the fictitious outputs are activated during this time interval. But after some time, when x1 tends to follow its nominal value, the role of the fictitious output vanishes and the error asymptotically converges to zero. So for the hybrid system, we have performed the simulation in the natural coordinates, and here the hybrid system behaves as a double oscillator where the main mode amplitude follows the transcritical bifurcation and given by the black solid lines, and the in-slave mode is damped, which is shown by this red solid line. So during the time interval 10 to 16 seconds, we apply a control input to the dynamics of X2 in order to excite the oscillator, and we can see the energy exchange between these two modes when the input is applied. Therefore, it forces the dynamics of x1 to 0, and the estimation is ensured when x1 is 0. So therefore, the proposed observer is well defined for singularity. And now I will conclude the results by giving the main points. So we have rebuilt the system, and the proposed high gain observer is able to handle the singularity in a good manner, and it is quite robust because we have limited the power of its high gain parameter up to the power of 2 regardless of the system dimension. So for the future perspective, the work is twofold. The first one is to do the experimental validation for the hybrid model, and the other perspective is to design the output feedback in order to bring the system to a symmetric wake flow, which is basically the promising way of energy minimization. Thank you so much for your attention, and for any questions, feel free to ask.